Good morning, students. In last lecture, we looked formation of partial differential equation by eliminating arbitrary constant. Now, in this lecture, we look formation of partial differential equation by elimination of arbitrary function. We have a function phi. This is an arbitrary function. It's a function of two or more variable u and v. So we have an equation phi u equals to 0, and we derive a partial differential equation from this given equation, where u and v are some function of x, y and z. Here z is dependent variable, where x and y are independent variable. So very first we are to differentiate given equation phi uv equals to 0 partially with respect to x and y. So when we differentiate phi with respect to x partially, first we differentiate phi with respect to u and differentiate u with respect to x, plus phi differentiate phi with respect to v and v with respect to x partially, because phi is a function of two variable u and v. So we use here partial derivative symbol del. And again u is function of x, y and z, so again we use del here. Now further we can write it del phi over del u into del u over del x. First x is function of x, u is function of x, then u is function of y, then u is function of z. But y is independent function, so del y upon del x become 0. This term becomes 0, and del x upon del x it become 1. So finally it convert into del phi upon del u upon del x plus p del u upon del z, and second term convert into del phi over del v upon del x plus p del v over del z, as v is also function of x, y and z. So both term convert into these term. Now from this equation we find the value of del phi over del u upon del phi upon del v, which is equals to minus del v upon del x plus p del v upon del z upon del u upon del x plus p del u upon del z. Similarly, now we differentiate phi, which is phi uv equals to 0, differentiate this partially with respect to y. And when we solve this term, we get del phi over del u is equals to del phi over del v is equals to minus del v over del y plus z del v over del z q del v over del z upon del u over del y plus q del u over del z. Just in previous equation here, replace x with respect to y. And now we compare equation number 2 and 3. Its left hand part is same, so right hand part must be same. So equating right hand part, we get this equation, and now we simplify this equation. When we simplify this equation, we get this equation. Here just we separate the terms of p, q and without pq term. When we simplify this equation, we get this equation, and when we simplify this equation, we get some term with coefficient of p, with some coefficient of q, and without p and q. So separate those terms having coefficient p, separate those terms having coefficient q, and those terms having no coefficient of p and q. So we can rewrite this equation as small p into capital P, where capital P is given by this term. Capital P is del u upon del y, del v upon del z minus del v upon del y, del u upon del z, plus capital Q into small q, where capital Q is del v upon del x, del u upon del z minus del u upon del x, del v upon del z is equals to r. R is given by del v upon del y, del u upon del x minus del u upon del y, del v upon del x, and small p small q, as we know, del z upon del x, del z upon del y. So this equation 4 is a required partial differential equation. Now we solve some problem based on this method, we are given a function phi of x plus y plus z and x square plus y square minus z square, and we are to construct a partial differential equation by eliminating this arbitrary function phi. As above we saw, phi is function of two variable u and v. So let's take x plus y plus z is a variable u, and x square plus y square minus z square is another variable, say v. So phi is function of uv, and we are given phi uv is equals to 0. Now differentiate this phi with respect to x. As we have discussed how to differentiate phi with respect to x, and when we differentiate phi with respect to x, we get this equation. So we can direct use this, or we can differentiate given equation. Del phi upon del x is equals to 0, we get this. Now here del u upon del x, u is x plus y plus z. So when we differentiate u with respect to x, we get 1. If you differentiate u with respect to y, you again get 1. When we differentiate v with respect to x, we get 2x. Differentiate v with respect to y, we get 2y. So putting value of del u over del x and del u over del y here, we get del phi over del u 1 plus p. Del u upon del x is 1, and del u upon del z is again del u over del z is also 1. Now del v over del x, which is also 1, and del v over del z. From here we can find del v over del z, which is minus 2z. So del phi over del u upon del phi over del v is equals to minus 2x minus pz upon 1 plus p. Again differentiate phi with respect to y, we get del phi over del u over del y plus q del u over del z plus del phi over del v over del y plus q del v over del z equals to 0. Del u over del y, as we have seen above, is 1, and del u over del z is also 1, and del v over del y, here del v over del y is 2y, del v over del z minus 2z. So putting the value of these partial derivatives, we get this equation, and when we rewrite del phi over del u upon del phi over del v, we get it's equals to minus twice y minus qz upon 1 plus q. These both are same. From equation 1 and 2, left hand part is equal, that's why right hand part must be same. So we get x minus pz upon 1 plus p is equals to y minus qz upon 1 plus q. Now we just simplify these terms, and we get partial differential equation x minus y is equals to p y plus z minus q x plus z. Now look another example. Eliminate the arbitrary function f and capital F from y is equals to f x minus 80 plus capital F x plus 80. Here we have two arbitrary functions, f and capital F. Now we are given the problem y is equals to f x minus 80 plus f x plus 80. Here we have two arbitrary functions, small f and capital F. We are to eliminate these two functions and get a partial differential equation. So first we differentiate y with respect to x. When we differentiate y with respect to x, first we differentiate f, which is any function, then we differentiate a second function, which is x minus 80. F is primary function and x minus 80 is secondary function. So first we differentiate f and then we differentiate x minus 80. So derivative of f will be f dash, and the derivative of this capital F is capital F prime. So del y upon del x is f prime x minus 80 plus capital F prime x plus 80. Now again we differentiate this y with respect to x. We get del 2y upon del x square f double prime x minus 80 plus capital F double prime x plus 80. Say this is an equation number 1. Now we differentiate given equation y with respect to t. We get del y upon del t is equals to f prime x minus 80. Now further we differentiate secondary function x minus 80 with respect to t, then we get minus a. Now second term plus f prime, capital F prime x plus 80 into a. Its partial derivative with respect to t become x, its derivative 0, its derivative a. So we get del y upon del t is f dash f prime x minus 80 into minus a plus f prime capital F prime x plus 80 into a. Now again differentiate del y upon del t with respect to t. We get del 2y upon del t square, which is equals to f double prime x minus 80 a square plus f capital F double prime x plus 80 a square. In equation 2, in right hand side we can take a square outside, then we have the term, remaining term is just same like the right hand part of equation 1. So we can rewrite these two equations 1 and 2 like del 2y upon del t square is equals to a square del 2y upon del x square using 1. So this is a required partial differential equation. Now there are some problem based on elimination of arbitrary constant and based on elimination of arbitrary function for solving. Thank you.